In this video demonstration, we're going to review how to solve a simple first-order lag equation. So the first-order lag equation is just about the simplest kind of differential equation you can get. We have a constant, which is known as our time constant of the process. If we're trying to solve for some generic variable y, we represent its derivative, and this first-order lag equation just looks like this. So let's look at what the different variables are. Tau is our process time constant. Y is going to be the output variable of our process. U is our input variable, and K is another parameter known as the process gain. So a Simulink makes it extremely easy to solve a very simple process like this. We use something called a transfer function. So a transfer function in Simulink looks like this. So you can see we have those same parameters. We have our process gain here. We have our process time constant. S represents a variable in the Laplace domain. If you've taken process control, this should be familiar to you. If you haven't taken it, don't worry about this. Just remember that representing a transfer function, if simple first-order transfer function is a block that looks like this in Simulink. So K over tau S plus 1, and I'll show you how to do that in Simulink. So we want to represent a very simple process just using sort of these generic variables. So I'm going to open up Simulink. I'm going to go to my library browser and go to continuous and find this transfer function model. I'll pull that in. So you can see it doesn't have tau or k in there explicitly, but we can go ahead and add those in. So I'm going to change this numerator to be my process gain, and for this generic process I'm just going to use a process gain of 10. So what this means is that for any change in my input u, my output will have a magnitude of 10 times that change in u. Our denominator coefficients, we're going to leave this second one just being 1, and we're going to change this first one to be our process time constant. Let's think about our simulation in terms of minutes. So I'm going to say our process time constant is 2 minutes. And now I just have this very simple transfer function model. So let's see what the response of this looks like. So remember, when we're solving this transfer function in Simulink, we're really solving this differential equation, and you'll see in later videos how this can come in handy for us. We could alternatively solve this differential equation using the same methodology that we've used to develop our tank and our reactor models by creating a function with the output being dy dt and putting in the integrated variable y as an input, putting in k and tau as parameters, and then putting in u as another input to our function and then solving it. But this method, using just a transfer function, will be a shortcut to that process. So if I go back to my transfer function, I'm going to want to give this some changing input. So I'm going to look at my sources. In my sources library, I'm going to choose a step change as an input. And then I want to view the results. So I'm going to go back to my library and get a sync, and I'll just find a scope. We just want to look at how the output of this changes. So I'm going to connect these. I'm going to simulate for 30 minutes, and I'm going to make a step change at t is equal to 10 minutes, and I'm going to go from an initial input of 0 to a final input of 2. So what we should expect to see when we simulate our system is that I'm changing my input u by 2 units, and I have a process gain of 10, so I should see my output change by 2 multiplied by 10, so 20 units. And then this 2 characterizes how fast that process changes from one steady state to another. So I'm going to come back here and run this. Okay, so we do see our process go from an output of 0 at this initial steady state to an output of 20 at its new steady state. And we can see that the process takes a certain amount of time, so it takes about 10 minutes to get from one steady state to another steady state. So, if you remember, our process time constant is 2 minutes. So one way to think of the process time constant is the time that it takes for our process to get from one steady state to 63.2% of the way to our new steady state. So if we zoomed in here, so 63.2% of our new steady state would be around a little over 12. So you can see here's 12. So about right here, we're getting to 63.2% of the distance from our initial steady state to our final steady state. And as you can see, it takes our process 2 minutes to get there. So we'll use this first order linear transfer function to represent some of the parts of our process where we don't really know how to explicitly model them using differential equations. So we can use this as an approximation to how those processes might work.